Okay, so as I said, we're going to do the practice midterm after this, so it's not that long. Those of you that have done the slides before know that there's only like 83 slides tonight, so it's not too long afterward, but we still have to get through what are called wood products. So we talked all about actual wood, but we're going to move into the realm of what is considered to be wood products. And it's pretty interesting how much this has changed in the last 10 to 15 years. I'm probably dating myself, and it's probably more like 20 years now. But we've gone from a construction industry that's based primarily in wood to a construction industry that's based primarily in wood products, right? And so I would say the bulk of the wood that's used today, right, is processed into manufactured wood products rather than just a solid piece of wood, right? And these are for a couple different reasons. One, it's to design engineering-wise the overcomings of basically the bad stuff that comes with wood, right? The shortcomings. I combined over and comings. Anyway, the shortcomings of wood, and the idea is that wood has defects in it, and can we find ways to minimize those defects? Can we find ways to remove those defects, right? The other thing is we want to use every single piece of the tree that we can, right? Because trees are expensive, and the more we can use of them and the less waste we have, the better it is, right? So we're going to talk through kind of a variety of wood products. I will show you more examples of these as we go forward in the actual construction. Today's just about the products themselves, right? So the first type of piece is what's called glue laminated lumber. And it's broken, so I have to be careful with it, but this is a really good example of glue laminated lumber, right? And I will pass around a smaller one so you can all see it, but I will use this as my example, right? And I thought I just organized this, didn't I? Apparently not. Okay, so glue laminated lumber, this is nice, and this is the one I'll pass around because it has kind of the rough end so you can kind of see it a little bit more. But the idea behind glue laminated lumber is that we're taking a whole bunch of pieces of lumber, right? We're putting glue in between them, and then we're pressing them together and letting the glue dry, right? And so we're making a beam out of much smaller pieces of lumber, right? So I'll start that one going around. And you guys can see this one as well. And you can tell, right, that we have a smaller beam there, but we can have really tall beams. And this one's actually, it's broken up here too. It was at one point taller. We're slowly losing our height to this beam, right? But it's a good example. So we're going to laminate because at a certain point, we just can't get a tree that's big enough, right? So if we think about something like this, that is a beam, maybe we need it to be 30 feet long, 40 feet long, right? Are we really going to have a tree that would be big enough to cut a beam out of 40 feet tall? It doesn't work, right? So we design, right, an engineered wood product to enable us to get that spanning capability, right, with a relatively cheap price tag, right? Sometimes we want to actually create a shape. We want a curve or an arch or something like that. We can do that same thing with glue laminated lumber, right, where we laminate individual sections together in a mold, and we can create the arc itself. And I'll show you some examples of this next class, right? The other thing about it is quality, right? And so because this is made up of smaller pieces, if there's a smaller piece, and I don't know whether this one has a finger joint in it, and I don't know whether the other one does. Somewhere there's an example of a glue lam that does. If there's a knot or if there's a bad piece in one of these 2x6s that makes up the glue laminated piece, right, we can cut that out, join the wood back together, and it will still maintain its monolithic piece, right? So we get the best quality structural lumber, right, because we're eliminating all the bad stuff. And so it's a really big advantage from a quality standpoint, which is why these things can span much further. Yeah? The glue actually increases the structural integrity in this particular case, right? Because of how we're putting those pieces together. It's a lot like when we think about like a wide flange, right, or an I-beam, right, where the top and the bottom chords are really the most important pieces. So we'll use the best quality lumber at the top and the bottom, right, and the middle ones don't do as much. So if we were thinking about this from a logical standpoint, we use the best quality pieces at the top, use the best quality pieces at the bottom, and the middle ones can be more fill, right? So those are the ones with the knots in them that we're going to cut out and that sort of thing. But we'll try to keep the top and the bottom stronger. And it's the combination of all those pieces being glued together that actually acts as the strength, right, of that overall beam. So most of the time, engineered wood products can span further distances and carry more weight than the same beam in solid wood. Right? So they're actually stronger. So, as I said, sometimes we want to be able to cut out knots. Right? Sometimes we need a beam that's longer than our pieces that are going to make it up. Let's say we want a beam that's 50 feet long. Okay? We want a really long spanning beam. We need to be able to join together smaller pieces of wood. So how do we do that? We already know that the laminations occur just in the layers, which is pretty self-explanatory. But if we're going to join these pieces because it's too long, right, we can use two types of joints. One is called a scarf joint, which is a really long taper. Right? The other is a finger joint. Right? And it looks like two fingers that are intersecting. Okay? The interesting thing about either one of these joints is they have about the same amount of glue area. Right? If we were to take this scarf joint and fold it back on itself, it would become the finger joint. Right? And the idea behind those is that instead of gluing two butts together, right, by joining, and this is kind of a principle of carpentry, all right, which is why we have more of the mechanical joinings that we do. But by increasing the amount of gluing surface, we end up with a much, much stronger joint. Right? And so we can do it in a scarf, we can do it in a finger joint. Doesn't really matter which one you choose, but that's how we can get rid of some of the bad pieces of the lumber. Right? Yes, sir. Yes, absolutely they can be structural. Yes, yes. And we'll talk about some of the ways that they're used. There are some issues with it if they are by themselves, just as a single piece. Right? We do have studs that are finger jointed together, which I'll talk about. They're not as common, but certainly in something like this, it's structural, and it's the combination of them. You wouldn't have it where there's a finger joint on top of a finger joint on top of a finger joint, right? You're going to stagger them, so that spreads out the load as well. Okay? So it can be laminated into virtually any shape that you want. It can be laminated into virtually any length that you want, both of which are a really good thing. Obviously, we have to transport them to the site somehow, so there are some limitations on it, right? And the defects can be cut out. The individual laminations are typically 1.5 inches thick. We're using basic 2x materials to create these. Sometimes in a small radius curve or an arch, we might decrease the size of the individual laminations and get down to like 3/4 of an inch, and that's just so that they'll bend in a tighter arc, right, than the 2x material. Okay? End joints are either finger jointed or scarf jointed. We just talked about that. And sizes range anywhere from 9 inches in depth to 75 inches in depth. Right? So they can be really tall, right? Which is obviously they can span much further. So we can move it one step further. And if we go back into the world of engineered lumber, glue laminated lumber was kind of the first type that was really around. And it's kind of obvious that it would be because you're taking relatively simple dimension lumber pieces, you're gluing them together, you're making a longer beam out of it. Kind of makes intuitive sense. Okay? But as we've gotten better with our other types of engineered lumber, right, or manufactured wood products, we've said, wait a minute, we can step up the glulam beam and make it even better, right, by substituting the top and the bottom chords of this glue laminated piece with a stronger piece of wood, right, or an engineered piece of wood. And so we'll substitute in a laminated veneer lumber, an LVL, right, instead of the solid wood top and the solid wood bottom. All right, and we'll explain what an LVL is in just a second. Don't worry. Right? When we put stronger members there, where most of the structural stress occurs, right, beams can be up to 20% stronger and 15% stiffer. Right? So we can make a really big difference on these beams just by swapping out the top and the bottom. Right? And so that becomes a hybrid glulam beam. Okay? Engineered lumber, and you've already heard me talk about engineered lumber, and I've thrown that name a couple times so far, right, basically means that it's lumber that's made from wood veneers or wood fiber strands and glue. Right? So engineered lumber is not technically a glulam because they're not pieces of wood that are glued together. They're actual long lengths of lumber that are glued together. But I would still wrap it into the engineered lumber. But this engineered structural composite lumber is where we're really starting to identify the most efficient ways of using our trees and get the strongest elements that we can out of it. Okay? So we're going to talk first about laminated strand lumber, right, and oriented strand lumber, right? These both types are made from shredded wood strands, right, that are coated with adhesive, right, and then pressed into the rectangular cross section that matches the size, the nominal size that you would be making for a particular beam. The LSL strands are longer than the OSL strands, and I'm going to show you some examples in just a second, right? It's the least expensive of the composite lumber, and it's mostly for rim boards or shorter spanning elements. Okay, and so let me get one here. Hold on, we have to. And I'm missing the LSL, and I don't know where it is. I'll have to find it. So, right, these are oriented strand lumber. It's this these technically are oriented strand board because I don't have my oriented strand lumber pieces. This is one of those things where I know they're in this room, but I can't find them, right? But the principle is the same. The idea is that it's just a little bit taller. But you can see the individual pieces, and I'll let you see that, right? And you guys can see this. There's a slight difference here, and we'll talk about the difference in a second, but it helps you to see it, right? Where we have these strands, right? These flakes that are then all glued together, right? You can see all the flakes being glued together. Excellent. Thank you. I knew it was here. Look at. Somehow I just missed these. Perfect. Okay. So you can still see the ones that I was passing around, but these will be a little bit better. Right? So they look very similar to the ones that I was passing around, right? In this particular example, this is the LSL. See how the strands are longer than the ones that I was passing around earlier, right? You guys haven't seen them yet anyway. See, the strands are a little bit longer, right? Also, all of the strands are oriented more in the direction of the board than in that they're a little bit more crisscrossed, right? And so these are generally going to be for the shorter things or like headers, that kind of thing. Notice that they can be bigger, right? Or they can be smaller, right? Depending on the structural use for them. I remember when these were first kind of coming out, being really weirded out that this was, you were putting a header in above like a sliding glass door or something, and you were using something like this, and it was like, that doesn't look nearly as strong as like a real piece of wood, right? But the truth is these are a lot stronger because we've taken a lot of the bad parts of the wood out, right? And we're using the best parts of the wood. Right, here I can throw this one over here. Parallelam is a brand name, right? And Parallelam is a brand name for parallel strand lumber, which we're going to get to in a second. Okay, so it's like Kleenex versus tissue, right? I'm going to stick with the non-brand names to the best that I can. Okay, so laminated veneer lumber is made from thin veneer sheets. And I have some of these. All right, you guys can start with this one. All right, and I'm going to keep this one, sorry, because I'm going to talk about it. Right? So laminated veneer lumber is made from thin veneer sheets, right, that are glued and laminated into thicker members. Right? So it means that you have really thin pieces, and we'll talk about plywood a little bit more. Right? This is the extreme example of a veneer. Right? But it's a really thin piece of wood, and we're going to glue these thin pieces of wood together, right? They look similar to plywood, right? Into the shape of a beam. So if we look at something like this, this is this laminated veneer lumber. It looks an awful lot like a piece of plywood, right? You guys are all familiar with plywood, I kind of assume, right? What? So why isn't this plywood? Great question. Okay. So if I look at this in contrast, and I'll pass this around again when we have plywood so you can see this a little bit better, right? But all of the grain direction is in the same direction, right? So if we look here, we can see the end grain that's been cut through. Every layer, right? Side grain, right? End grain. Consistent, layer to layer to layer. So it's going to span only in this direction, not in this direction, right? So we're not going to lay it flat, right? Which is why this is stronger. So basically what this is it's a piece of plywood, right, where all of the grain is running parallel. All of the veneers are running parallel, as opposed to alternating layers. And you'll see this clear as day when we get to the plywood section, right? And I'll pass this around again. So there's your laminated veneer lumber, right? These are longer span headers, right? They're getting into the realm of beams, right? And so depending on what you're building, you're going to use some of these, right? Some of the parallel strand, some of the paralams, the parallel strand lumber, which we'll get to in a second, and some of the oriented strand lumber, the OSLs, right? So parallel strand lumber is different. It's made from long, thin strips of wood that are glued together. Right? Here's your sample that you guys can pass around. And this is the one I'm going to keep. I like it when I have 3 samples, right? So it's made from long, thin strips of wood, right, that are glued and pressed together in a process that's very similar to an LSL or an OSL, but the uniform strips are arranged more parallel, right, than the OSLs or the LSLs, right? They're often for longest spanning beams, right, that kind of thing, right? So if we look at these, parallel strand number, I just want to make sure I have this right? Yeah, good. Question? It's how they lay them in a form. These are basically made kind of like concrete, where they're put in a form, right, with the glue and the resin, right? And so they're pressed in multiple directions to keep them parallel. And if one of them were off when they mechanically put them in, it won't work, right? So if we look at these, right, and we look at all of these individual pieces, they look kind of like worms on the end, but those are all these long, long strips, right? And they're much longer strips than the pieces that you'll see, right? And they're glued and pressed together to form this beam. Now recognize, if you look at something like this, there's no knots, right? There's no checks. There's nothing strange that's going on in these individual pieces. So we're maximizing the pieces. Furthermore, think about the size of the tree that each one of these pieces could come from. It could be a relatively small tree, right? So we're using the most of it. Likewise, you know those edge pieces when we were talking about sawing the lumber, right? All those edge little waste products, right? Here's a bunch of, you're not wasting that stuff anymore, right? So we're engineering these together to provide better structural integrity, okay? So these parallel strand lumber ones, which look kind of the weirdest, are actually the strongest, right, of their classifications. We worked our way up, right? They're also the most expensive, right? So again, longest spanning things, okay? The other thing that we can do is we can make what are called I-joists, right? And this is definitely kind of in fashion now. Most buildings are made with these, right? And I have a couple different examples of these, right, that we'll pass around. Okay? And so these work just like wide flanges in steel, right? Same concept here. The flanges, right, are solid wood LVLs or LSLs, right? And if you look at the variety of flanges that I pass around, like that one's a solid piece of wood.
So it's manufactured and then they just cut it to length.
Exactly. This is all manufactured at a shop. The webs, right, are going to either be OSB or plywood. That one's plywood. This one's OSB, right, which we'll talk about what OSB is in a second. And so what we're doing is we're using the wood in its most efficient manner, right? On the top and the bottom, right, that's where we need the wood the most. The web isn't doing much, just exactly the same as steel would be doing, right? It's just keeping the top cord and the bottom cord separate. Therefore, this is very efficient, and it's also, if you think about it, it's very cheap and very light, okay? So generally speaking, right, people will choose to use these because they're easier to work with. They can span a further distance, and if you don't have a lot of headroom between your floors, right, you can actually shrink down the size of the lumber that's necessary, right? There's one little one that I'm passing around that can probably span as much as a much taller piece of solid wood lumber would be able to span, right? So these are very, very common, right? It's using the wood more efficiently. The other thing is, because these are nowadays all engineered, right? OSB, LSLs, right? They're not going to shrink. They're not going to move. They're not going to warp. They're going to stay exactly the same. So your floor is going to stay perfectly level, right? The only thing about them, and I will tell you this side note from experience, is that they're springier than normal wood. And so if you're up on a second floor that's made with these, you'll notice a little bit more spring in the floor, right? Especially if they're longer spanning. If you have supporting walls and stuff, you won't notice it. But if you have a large open room that's on a second floor, they spring a little bit more. Yes, sir. Yes, much less likely to get squeaks. I would argue that it's still theoretically possible to get a squeak, but much less likely. Right? I think that was a way of marketing it. Well, I think a lot of them still say silent floor on them. It's a brand name thing. You have to think about how people want to try to market things. And I think if you were trying in the beginning of these to sell these instead of regular lumber, people would be like, why am I wanting to do it? Now they're going to use these more for structural reasons than anything else. Yeah. Yes. Yes, yes. Because you can get more structure out of the same depth, right? I think it's very, very likely that where in an older building you'd have a separating wall or a beam that would support one side and the other side, now you're going a much larger span and you're getting a little bit more spring for it. So, very common in construction. And we'll talk about like the circles that are already pre-cut and stuff when we get down the road. I can't give you too much about this today. Okay, so before we go on, I want to take one little side note, and that is to talk about, yes, this is really great, right? But there are some problems with using this engineered wood. Recognize that you have a bunch of glue that's holding these things together rather than a solid piece of wood, right? And so you've got a couple problems with that. One, if any of these pieces get wet, you have unless the glue is waterproof, which some of them are, you have a problem, right? Because they can delaminate it and lose their structural value. The other big problem is in a fire, right? If you have a solid piece of wood, it takes a lot longer to heat that wood to a point where it will actually ignite and catch on fire, right? These pieces are built of smaller little strands of wood. It doesn't take as much to heat one of those little strands of wood to a point where it will catch on fire, right? So they tend to catch fire a little bit easier. Furthermore, when they catch fire, the burning of the glues can be much more toxic than a traditional wood frame building. And I've actually heard of some firefighting departments saying we won't go in newer structures the way we would go in older structures because we can't predict how quickly they'll fail, right? And because it's much more toxic than it used to be, right? And so there's some downside to all this engineered lumber, and I'd like to at least include that so you're thinking about that a little bit. It doesn't mean that if I were building a structure, I wouldn't use engineered lumber. I still would probably use engineered lumber, but it's certainly something worth thinking about. Okay? So that leads into what are some of the advantages and disadvantages. I've already given you the kind of the big disadvantage. How about some advantages? Strength, weight, longer lengths available. It's more economical to produce, right? Somebody said truer, right? Which basically means that it's not going to twist and warp the way it would be, right? Did I skip a slide? Structural finger jointed. I did skip a slide. That's my fault. So let's jump back really fast, right? This is what we were talking about those finger jointed pieces, right? This does exist. When this happens, it's primarily for studs, right, in a wall. They're the vertical elements. And the reason that it works is the weight tends to go down through them. So you're stacking one on top of the other. If you were spanning something with finger jointed, the finger joints themselves would have a tendency to break, right? So it only works because the weight is going down. So they're only going to be for studs and posts. Yeah. Absolutely. Right. Finger jointed pieces, or anytime it's going to be painted, right? Typically, it's going to be finger jointed because you can't see it once it's painted. But that's a non-structural use. Okay, so here's my list, right? So we got adhesive off-gassing, we've got fire danger, right? These are basically the reasons that we've already talked about, and it should be relatively self-explanatory. Though you do know in a lecture, when I ask a question like that, it usually means it's going to show up later, right? Okay. So now we get into the really goofy stuff, right? So we're going to talk about wood plastic composite decking, right? And so this is, anybody heard of the brand name Trex, right? This is Trex, right? And so I have an example. This particular example isn't Trex, but this would be considered a wood composite decking, right? It's made from wood fibers, right, and plastics, right, and other chemicals, and then it's pressed and molded into a shape that looks somewhat like wood, right? And you probably throw in a little bit of dye to make it colored like wood, right? And you end up with something like this. It is incredibly consistent in its material quality, right? Every piece looks exactly the same. It is extremely resistant to moisture because a large part of it is made of plastic, right? The problem with something like this is it really doesn't have much structural value to it, right? Because it's made up of such small little pieces. It does, however, have its place in decks, right, which is kind of what Trex was originally designed for, or exterior things where you don't want things to deteriorate. You want the color to stay true to the wood. You don't want to have to stain it, etc. I don't think that Trex is the best for color resilience, though they've gotten much better than the original Trex. They've also gotten better at putting patterns on it so it looks more like lumber, or putting patterns on it so it has a little bit more grip to it. Right? The truth is that Trex is a really interesting, innovative product, and certainly has a place in buildings. I think the problem is they value the product a little bit too high, and this is my personal opinion that I'm adding to this. They value what it is a little bit too high. You would pay a similar amount for something like Trex that you would pay for redwood, or that you would pay for a Brazilian hardwood. Right? It's very expensive. And go to Home Depot. Right? Go to Lowe's. They'll have Trex and they'll have redwood. Compare them. Right? They're usually within a couple dollars of each other. And I think it's unfortunate because this is certainly not something that costs that much, but the companies that are making these products feel like they can charge that amount, right? Which is kind of too bad. I think if it were less expensive, we'd see it everywhere. And so, in time, companies may start lowering their prices, right? So this is a wood plastic composite decking, right? Kind of a weird thing, right? We have non-structural composite lumber, right? These are blends of plastic and wood, right? Where the qualities are going to vary depending on what its intended use is going to be, right? It's often used for trim, right? Those kinds of things where it's going to be painted. I don't have a particularly good example of this, but if you're in the molding section at Home Depot, there are certain types of their moldings that are this kind of, it's like a plasticky wood. It's not Trex. It's more paintable, but it's definitely not MDF or pine, right? It's kind of that in between. I don't have a good example of it here. I apologize. Clearly, I have to go to Home Depot and get a sample for you, right? It expands and contracts a bit with moisture because it does have the wood in it as well, right? We can move all the way up into the realm of plastic lumber, right? Which is really weird, right? And so here's an example of plastic lumber. It looks like lumber because they put grain on it so it looks nice, right? But it is completely synthetic, right? And therefore it won't rot and it won't change and it won't shrink or anything like that, right? It has very little structural value at all, right? But it's really good for things like trim and things where you don't want to have to replace them and you're going to paint them and it doesn't really matter, right? Of course, it's resistant to water, insects, right? Fading, those kinds of things. It's plastic. It's recycled milk and that sort of thing, right? It's going to be used for decking and trim and that sort of thing. So let's move from the weirdness. Oh, I have to pass one more around. Where's this one, right? This is like one of my favorite pieces of molding, right? It's some kind of rubberized flexible molding, but it's like completely bizarre. And it would fall under these categories of untraditional lumber. But I have to pass it around just because it's goofy. Okay. Yeah, you paint it. Obviously, it wouldn't have the lettering on it. That's the sample, right? So wood panel products, okay? Wood panel products are basically what plywood was, but it's evolved into a much bigger industry than just plywood, right? Panel dimensions are typically 4 by 8, right? They require less labor to install because they're in larger pieces, right? They're resistant to shrinkage, swelling, checking, splitting. That has to do with how they're made. And they're very efficient in their use of forest products. So there's three types. The first type is plywood, which we'll talk in depth about in a second. We have composite panels, and then we have non-veneered panels. And we'll talk about each one of these in depth. Let's talk first about plywood. Right? Plywood is made of thin sheets of wood veneers that are glued together. Right? The grain on the front and the back of a piece of plywood are always in the same direction. And so this is the example. I'll pass this around. This is a veneer. This is thinner than the veneer you would use in plywood. But this would be a veneer, like let's say you had a piece of plywood that had a thin veneer of a hardwood on it so that you could have the look of hardwood for a cabinet or something like that. This would be the thickness of that kind of a veneer. But it helps illustrate the concept of veneer. Right? And I'm going to pass around a couple pieces of plywood. I'm going to keep this one. You guys can have that one. And you guys can have this one. Okay, so the grain on the front and the back run in the same direction. So if I'm looking at this piece of plywood, right, I see the flat grain running this direction. If I flip it over, I see the flat grain running this direction. Right? It's always the same on the front and the back. Furthermore, if I count the number of layers in plywood, it's always going to be an odd number of layers. So you guys can see there's the flat grain here. We've got flat grain on this side. They're both running in the same direction. Okay? You guys can see it too. There's your flat grain. Flip it over. That's the flat grain as well. Right? One or more of the interior cross bands, so one or more of the interior layers, is going to have grain running in the opposite direction. Right? So it's perpendicular. So I have grain running this way and this way on this piece of plywood on the surfaces. And if I look at the layers, right, I can see on the edge that there's one running this way. The next layer is running opposite. The next layer here is running this way. The next layer is running this way, right, etc. Right? Do you guys see that? Where we've got a layer running this way. The next layer we're seeing end grain, which means it's running this way, right? And then we alternate. Right? You guys see it? Grain running this way. This next layer in here is running the opposite direction. Then this layer is running that way. You guys got it? Right? Same way here. This is running that way. The next layer is running this way. Let me tip this down so you guys can see. Yeah. Right. So the grain's running this way in this piece. The next one, the grain's running this direction. Right? The next layer is running this way, which is why you can see all the layers in plywood. Does that make sense? So if you go back to the laminated veneer lumber, right, which looks like the sheet of plywood, this just helps illustrate it, right? If we're looking at the two end grains together, right, we see that it's either all end grain or all parallel. We don't have the opposite, right? Laminated veneer lumber. Right? Microlam is one of the brand names for it. That's why it says Microlam on it. Okay. So the key thing about it, always an odd number of layers. Top and bottom are always in the same direction. One or more of the interior crossbands is going in the opposite direction. Right? And so depending on the grade of plywood, you might have 3-ply, which is just 3 plies. Right? You might have something all the way up to 11 or 13 ply, right? It's a lot of thinner layers, right? So composite panels, right, have two parallel face veneers bonded to a core of reconstituted wood fibers, right? And these vary a little bit. I have some examples of them. Plywood. Okay, here's a good example of it, right? Well, this is more of a laminated, but it's the same concept, right? You have an outer veneer and two outer veneers, and you have a reconstituted wood fiber core, right? I think I have one with an OSB. This one's pretty good. This one's hard because it's red, so you can't see it as well, right? But this one has 3 plies here, the middle, and there. But if we look carefully at this inner core, right, those inner 2 layers are reconstituted wood fiber, like an OSB. Here, I'll pass this. This one. The red one's kind of hard to see. Right? Then we have non-veneered panels, right? Oriented strand board is the most common, and I passed those around a little bit earlier. Here's another example of that, where the core is weird. Where were my OSBs? Under here. Okay, so this is my oriented strand board, okay, which is a non-veneered. It doesn't have a skin on either side of it, okay. We can see the oriented strands in it, right? Has long threads of woods that are compressed. I'm going to turn the light on so you guys can see this stuff a little better. Can you see the screen okay if I have the light on? Okay. So it's generally stronger and stiffer than the other types of this non-veneered lumber, but this still, the important thing about OSB is it still has layers, just like plywood, right? And if you look really carefully, and I'm going to pass these around again so you have to look at them, right? You can still see the layers where we've got a set of grain that's running this way, then we come in here and we have a set that's running this way, right? So even though they're flakes of wood, right, you guys can see if you look at the edge, and I'll pass this around so you guys can see it, that there are those same layers that are alternating, right? You can look carefully and kind of see the layers as they go through, right? So I'll start with you guys. You can pass it around. Where was the other OSB? It's here somewhere. Oh, there you go. So you can see the same thing there, right? So oriented strand board, or OSB, very, very common in building construction, right? We're going to use it just as we would use plywood, and it tends to be the strongest, stiffest type. Particle board, which you're probably somewhat familiar with if you've ever bought furniture from IKEA, right? Is similar, right? Except it's made from smaller wood particles that are compressed and bonded right into their panels. And so I have a couple examples here that I'll pass around of particle board, right? It's very much like OSB, but it's much smaller. Likewise, if you ever made IKEA furniture and perhaps sat on it wrong or something like that, you may have noticed that it breaks much easier than OSB because the particles are much smaller. Right? This is manufactured in different density ranges, right? So depending on how dense it is, it has increased or decreased strength. It's a very classic example as a base material for wood veneers for furniture, right? Which is basically, think your IKEA table. That's exactly what it is, right? We're filling up the space to make it look like wood, and we're covering it with a veneer so that it looks like wood, right? But it's not. Fiberboard, right, is made from wood fibers and synthetic resins, right? And I do have, right, here we go. Here's a piece of crown molding, right? It's intended for interior use only. It's dimensionally more stable than particle board, right? It's a little bit stiffer and better able to hold fasteners because it's denser, right? The most common type is MDF, or medium density fiberboard, which is going to make a lot of these moldings, right? The nice thing about these kinds of moldings, and I will pass this around, I don't have a lot of examples of MDF. I know, you would think, right? Most of the sample trims and stuff are all pine, so whatever. Anyway, the MDF, the nice thing about an MDF is it can be pressed into a shape like a crown molding very, very easily, depending on what mold. So if you want something a little bit fancier, if we look up here at the moldings, those happen to be pine. But if you want something fancier, you don't have to run something like this through a router, right? You can actually press it into its final shape. And it ends up with a very good quality, smooth surface, right? The problem with something like this is if it gets wet, it swells, right? So if you have a newer house where you have MDF baseboards or something in, say, a bathroom, right, and you've ever gotten those baseboards wet, you'll notice really quickly that they swell up, right, and they can cause problems and they can look kind of ugly, right? In that instance, I would recommend, right, doing the rest of the house in MDF because it certainly is cheaper and it's very nice to work with, right? But when you get to the bathroom, buy pine moldings and put them in because they won't swell the same way, right? And so you can get the same looking thing that's upside down, the flutes on the bottom of the crown. Okay, so let's talk a little bit about plywood production, right? A big log is soaked in water, right, to soften it up, right? And then it's rotated on a very large lathe, right, and a knife blade is put against one edge of this log, right? When that happens, the thin little veneer, right, is peeled off. It's kind of like unrolling a roll of toilet paper or paper towels, right? You have a thin layer that gets unrolled and peeled off, right? And that paper, right, or that thin veneer is then used, and it varies in thickness depending on what you're trying to make, right? But that veneer is flattened out, right? It's clipped into its rough shape, right? It's dried in a kiln down to 5% moisture, so it's very dry. Then the sheets are going to be assembled into larger sheets. The defects are going to be gotten rid of, right? Then we'll take one sheet with the grain running in one direction. We'll take a sheet with the grain running in the opposite direction, and we'll stack them up, and the machine will spread glue on them. So there's not a person out there with a big glue bottle squirting it on, right? It's a machine that spreads out the glue, right? And then they're going to be pressed together, right? So that the stack is all compressed, right? We get good glue bond, right? And we're going to add some heat to help the glue cure really quickly and nicely, right? And finally, the panels are going to be trimmed to their appropriate sizes and shapes, right? So it makes some sense for how this stuff is actually produced, right? Plywood is going to come in a thickness anywhere between 1/4 of an inch and 1 1/8 inches in thickness. Some of the sheets I passed around are a little bit thicker. This one's a little bit thicker there. Actually, this has a reconstituted wood fiber core too. This is a good example of that. So, but anyway, you can get them thicker, right? And you can get them thinner. Usually it's more of a finish grade, right, that has a veneer. I don't know who said it, so I don't know who I'm talking to. You did. It's more of a finish grade, so if it's an 1/8 inch plywood, it's not going to have as, it might be 3-ply. Most often it's just, a core and one grain and another grain laminated together. So for true plywood, you're looking at about 1/4 inch, so you can have those 3 plies. Right? So medium density overlay plywood, right, is for an especially smooth surface, right? And I have one example of it, but I don't know what happened to it. Right? This is an MDF example. I don't know. It's one of the sidings, right? And where you're putting a little bit of a synthetic product over the top of the plywood to make it look nicer, right? Oh, I know where I have this. This is, one of the resins. This is most common for formwork, right? So if you're going to do something where you're going to cast concrete against it, right, you might put a resin on top of this, right, to make it extra smooth. So this was back in the formwork days, right? But this is plywood. The grain's going in the opposite direction, but it has that nice coating on it for the concrete, right? Unlike structural paneling, so interior use. This is if you have. Sorry, I have to catch up with where I am here. Do I have a sample of this? Not really. So this is for interior grade where you're looking like to make cabinets or something, where you're actually using real plywood with a real veneer on it, maple veneer, an oak veneer, something like that. You're taking that very thin veneer, right? But since you care about the grain structure, maybe you're making fir cabinets and you want them to be vertical grain fir, right? You're taking those quarter sawn pieces. Remember when we cut the quarters, the log into quarters, right? And we're slicing those quarters and we're piecing those together instead of unrolling it, right, as a large sheet. So it's giving you a little bit better, higher quality grain structure, right? So we can move into another type. The really crooked board is the best example I have of pressure treated. Here, so we can pressure treat wood, right? We're designing to counteract the susceptibility of wood to decay with water or to have insect infestations, right? And so the first type that was used to do this was creosote, and this is very common for railroad ties, right? Or garden beds sometimes, light posts sometimes. It has a very, very distinct smell, this kind of oily smell. I kind of like it, but that's, some people are kooky and like the smell of diesel and whatever. It's just one of those smells. Anyway, it's probably completely toxic, and I shouldn't be smelling it. But anyway, it has an odor, right? It is toxic for the environment. You can't paint it, which is problematic, right? And so nowadays it's very infrequently used. You still might see it in railroad ties, but that's about it, right? Then we came up with pressure preservative treated lumber, right? The older kinds were green. We've now switched to brown pressure treating, and that just distinguishes a difference in the chemicals that were used. The type that was green was chromated copper arsenate, and basically what happens, and you can see in a board like this, there's a bunch of these little slits that are cut in it, right? Those slits are the injection points where they inject the wood with the chemical, right? And so this is your basic Doug fir, right? But it's been injected with this chemical, and the older chemical is this chromated copper arsenate. Unfortunately, it had arsenic in it, and we tended to use it for like playgrounds with kids and that sort of thing. Bad idea. Determined that was too toxic, so it's been phased out in favor of lumber that's treated with specific types of salts and or copper, so that they don't have the arsenic in it. The newest set of pressure-treated lumber that is being used now reacts badly with nails and metals. So now we're going through a rash of, yes, the wood is safe to come in contact with, but all the nails and stuff that hold it together are starting to fail. So there's problems with this stuff. Anytime you're trying to counteract nature, we can run into these sorts of things, right? But you can get some long-term protection, up to 30 years, from these kinds of pressure impregnations of chemicals in wood. Yeah. The green, no, it's the dye that's in the chemical. Right? It's just like now they make it brown. They just add a dye so that you can more easily distinguish that it's pressure treated. Okay? The other alternative, right, if you want decay-resistant wood, is to use a type of wood that's naturally decay-resistant. So if you use redwood, for example, or you use cedar, would be another example of naturally decay-resistant wood. Right? So you don't have to use it. It was kind of interesting, and I happen to have current knowledge of this because over spring break I was working in my backyard, and I was doing some new borders for a play structure for my daughter, and I priced out the difference between pressure-treated lumber and redwood. Right? Now, recognizing that the redwood that I was picking from, and this was just at Lowe's, so you guys can all go there and look through the stack that I looked through. The redwood was common, so it wasn't particularly good grade redwood. It had knots in it and whatever. But if you pick through the palette, you're going to find a few decent boards out of it without too much of the sapwood in it because the heartwood's more resistant and what have you. Anyway, for a similar board, so let's take a 2x6x16, right? I think that was somewhere in the neighborhood of $14 or $15. Okay, same 2x6x16 and pressure treated, it's like $12 or $13. So there's really not that much difference in price, right? And so it used to be a much broader difference in price, which is why you'd go with the pressure-treated lumber over the natural product, right? So I throw that out there just as a comparison, so if you're thinking about it. Obviously, with wood, we have to find a way to fasten the wood together. We have to be able to attach wood pieces together. We can't weld wood together. We need some way of attaching it. So unfortunately, these attachment points are always the weak points in the linking the wood pieces together. And so when in doubt, we tend to rely on the fact that one member can rest on another member, and that's a good connection. Right? And you'll see that when we talk about heavy timber construction and light wood framing, we rely on that a lot, right, as opposed to the actual metal connections. Okay? We do have a variety of types of fasteners. Nails would be the most common. Basically, I'm assuming you probably all know what nails are, I hope, right? It's a sharp-pointed little metal pin, so to speak, that we're driving into the wood either with a hammer or with a nail gun. Thank God for nail guns, right? Back in the day, people didn't have nail guns, and they spent a lot longer in construction. Now, nail guns are just all over the place, and you're, of course, going to use a nail gun whenever possible. Nails are come in a variety of types. You can see a variety of types here, right? Here's a whole other set of variety, right? We're not going to get into how do you classify nails and such, right? There's kind of a weird classification for nails, but it's too much for the scope of this class. We have a couple different ways of nailing wood. A face nail is where we have one piece of wood and another piece of wood side by side. We nail through the face of the wood, right? An end nail, we're nailing through the face here, but into the end grain, right, of this piece of wood. So it's a T connection. And the last type is what's called a toenail. So instead of an end nail here, we're toenailing through the bottom part of this wood into the other piece of wood, right? And we'll use these types of connections throughout the rest of construction. An example of a nail gun, if you haven't had the privilege. So I will end with a question before we get to the midterm practice. Do you think wood is a sustainable building material? Yes. Okay. Why? Somebody speak up. Speak up. You're all mumbling, but you're all on the right track. Yes.
The reason is because we've been able to, with our technology, be able to keep our forests. We harvest them better, and then we've also been able to find other ways to use more of the wood in different products. And then when we take things down, we reuse that wood again in other products. So it's sustain. It seems to be the most sustainable.
I like it. I like it. I think it's a good argument. Anybody want to add?
Farming, the way some places now they're actually setting up farms for trees, and then instead of just going out in the forest, they've got all this acreage that they literally have the trees set up in rows, and then just go through and get them when they're ready.
Yep. Right. You're consuming the material rather than being able to replenish what you have. Would anybody argue that it's not sustainable? Okay. Sure. I mean, they can certainly. I mean, we can have wood buildings that last a longer time, but there is a certain level of permanence. I mean, I think I've told you guys before the average life of a track house, 30 years, right? So that would be an example of a not particular sustainable use. The failure of the wood being the cause of that might not be as relevant as the really poor quality of construction, right? So it might not be the material itself that's failing, but sure, I think that's a valid argument. Yeah, no, it's not uncommon. If they're well cared for and they have good interior and exterior finishes, the wood can last for a very, very long time. Yes and no. There are certainly some advantages to light wood frame construction, and we'll talk about the advantages of light wood frame versus heavy timber. And so you're going in the direction of what the next couple lectures will be about. But in terms of sustainability, not as much. I don't think it's as valid of an argument for sustainability as it is for why you might choose one over the other of the wood building method. So anyway, there isn't, of course, a right or a wrong answer for this question, but the book tends to emphasize this sustainability thing. And so I think it's important to at least touch on it. And I think the more you know about these materials, the more you can really understand why this might be a more sustainable material, which is what makes it a good question. Okay? So we'll go from there into the practice midterm. Yes, it does make it a very good test question. Right? And you guys kind of learned from the last midterm that the types of test questions that I love to ask in the essay section are, give me 3 advantages or 3 disadvantages or 3 reasons, right? And generally, I think I'm pretty reasonable about what those 3 reasons might be, right? Okay, let me stop this.